Welcome to Calculus. Today we will investigate the squeeze theorem, focusing on how if a given function has y values that are always between the y values of two other functions, then given that the limits of the upper and the lower function are equal as x approaches a certain number, then the limit of the squeezed function equals the same number. Let's head over to our examples. Let's head to our notes. So we've got our first function to consider here, squeezed between two other functions. Let's state the squeeze theorem again, just so that we have it in our minds how that works. So we've said it in words in the intro there. What we want to do is catch what it looks like algebraically and then graphically. So I'm going to say I have two functions. So the first one's here, g of x, and its y values are somehow less than values of another function h of x. So that's part of the condition of the squeeze theorem, is that this h of x always is above g of x. So on a graph, if I were to start to draw it in, let me put the plane there. And then these are kind of generic functions, so I'm just going to put something kind of generic itself. Let's say that's h of x, so all of its y values are above the y values of g of x, except maybe at one point they might have equal y values, and that's okay. So when I write the expression, I am going to put, or the inequality, I'm going to put the equals option. So let's say that that's the case, but that there's also a third function, f of x, that's between those two guys always. And again, we're just saying that the y values of f of x are always between the values, y values of h and the y values of g. So it might look something like that. So graphically, that's our setup. The extension to limits goes like this. So let's say that I know that the limit as g of x, I'm sorry, the limit, and let me get that in the proper notation. So LIM, as x approaches some c value. So here on our graph, what we'll consider is, hey, let's say that that's c. We don't quite know where that is. Looks like it's at the origin, but it could be anywhere in the x-axis. If the limit as x approaches c of g of x equals some number L. So again, that's a y value as x approaches c of this function g of x. And if I also claimed that the limit as x approaches c of h of x also equals L, which kind of is represented here in our graph, that y value where both those graphs are meeting is L. Then the claim that I can make is that the limit as x approaches c for f of x also equals L. Now this is particularly useful if finding the limit of that red one, f of x, is difficult, if it's not easy to do algebraically. But if I can come up with two other functions, one above and one below, then I can apply this squeeze theorem. Well, let's look at it in action here with some actual functions. So here I've got the task of using the squeeze theorem to find the limit as x approaches c of f of x. And I'm told that c is 1, so I'm interested in finding the limit as x approaches 1 for f of x. Please notice that I'm not given an equation for this function. I'm just told that I need to find its limit as x approaches 1. I'm also told this, that this function on the left, so let's kind of situate it as g of x. So that's x minus 1 squared plus 2. I'm going to graph that. So over here on the right, in fact, let me use the green for the plane, and then we'll distinguish the function by putting it in the purple. So the plane is in green. And I want to graph this function x minus 1 squared plus 2. So that's a quadratic that's just been translated. Remember that minus 1 on the inside means that it's been translated 1 to the right. And the plus 2 means it's translated 2 up. So I'm going to find the point 1, 2. And then I'm just going to draw the parabola same as the parent function. It's just been shifted, translated across the coordinate plane. And that's g of x. I've also got, if we think in terms of our original way that we defined two theorems or two functions to squeeze another, this will be our h of x on the far right. It also is the quadratic parent function. It has been shifted 1 right, 2 up. But it's also been reflected in the x-axis. So one way we can view that is that it's gone from a parabola that opens up to a parabola that opens down. But its vertex is still at the point 1, 2. So if I consider this graph, it's something like those two functions. Now, we don't know anything about h of x. I'm sorry, about f of x. It's some mystery function, but what we know is that its values, its y values, are always between the y values of the purple g of x and the blue h of x. So to apply the function, really what we need to find is what's the limit of g of x as x approaches 1? What's the limit of h of x as x approaches 1? Well, we can kind of see it there on the graph. Just to kind of make a case, the limit as x approaches 1 for this upper one is the same from the right and the left. The limit should be 2. So the limit as, in fact, let me write it over here to the side. For g of x, the limit as x approaches our c value is 1. Looks like it's 2. Let's verify that algebraically though. So I'm going to pull the function x minus 1 squared plus 2. So remember, when doing limits, you want to start off, try to do direct substitution. So this is going to be 1. I'm substituting for x, minus 1 squared plus 2. 1 minus 1 is 0. 0 squared is 0. 0 plus 2 is 2. So the limit of the purple g of x on the left is 2 as x approaches 1. So the graph's supported by the algebra there. I also think the same is the case for the blue one. As x approaches 1 from the left and from the right, the y value there is the same. It looks like 2. So let's see if that algebra is also supported. The limit as x approaches 1 for this blue h of x is negative parentheses x minus 1 close parentheses squared plus 2. So again, I'm going to directly substitute 1 for x. So that's negative 1 minus 1 squared plus 2. And the negative sign doesn't do much because still 1 minus 1 is 0. 0 squared is 0. Negative 0 is 0. 0 plus 2 is 2. And so I see that the squeeze theorem is applicable because the limit as x approaches 1 of g of x, that purple one, equals the limit as x approaches 1 of h of x, and we know that that value is 2. To apply the squeeze theorem, it's also called the sandwich theorem, all we have to do is say at this point, well, if our function's always between those two, and their limits are equal as x approaches 1, therefore, logically, according to the theorem, the limit as x approaches 1 for my mystery function f of x also equals 2, and that is case closed. Nice application of the squeeze theorem or the sandwich theorem. Let's take a look at one other example that's a little less numeric. So it's a similar use of the squeeze theorem. I want to find the limit as x approaches c for f of x. But whereas in the previous example, I had c equals a number, here I'm told c equals a. I'm not sure where that is. The forms of the function left and right are still the same. So if I think that this one on the left is g of x, and this one on the right is h of x, let's keep our color coding consistent. And we're making a claim that f of x, its y values are always between the purple and the blue function. I can't specifically graph where the purple and the blue function are, but I can put them in a way that's just kind of roughly there. So if I think in terms of transformations again, this one's been shifted right a terms, and it's been shifted up b units. So if I were to graph that one, let's just say, I don't know, we're going to say that that's been shifted to the right a units, shifted up b units. Well, that graph is still going to be the quadratic parent, just shifted. I just don't know how many it shifted right, how many it shifted left or up. Same for this other one. It's got the same key characteristics as the first h of x we saw, but without numbers here for the translations. So again, generally speaking, it's been shifted right a. It's been shifted up b. It has been reflected in the x, so it also faces downward, reflected in the x-axis. So again, it has the shiftings a to the right, b up, opens downward. So even though I don't know a whole lot about the specific a and b, I can kind of just think conceptually, well, it's been moved over right a units, moved up b units. And all of the f of x values in red are between the two functions. So my thinking is that we need to say something like, as x approaches a from the left and the right for g of x, looks like it's getting close to the y value of b. Also looks that way for a there. Well, let's see if the algebra again supports that hypothesis. So the limit as x approaches, I'm just going to say a, of x minus a squared plus b. Let's go ahead and solve that. So I'm going to try direct substitution. That is a for x minus a squared plus b. A minus a is 0. 0 squared is 0. 0 plus b is b. Let's see what the limit for this one in blue is. So the limit as x approaches a of negative x minus a squared plus b. That's no harm in trying direct substitution. So negative, substitute x with a minus a squared plus b. And again, this shows the same features as our first example. A minus a is 0. 0 squared is 0. Negative 0 is 0. Plus b is just b. And so at that point, what we can claim, really we can invoke the squeeze theorem by saying the limit as x approaches a for g of x equals the limit as x approaches a for h of x. So I'm just calling the whole function by its function notation. So I've got the specific equations here. And it equals 2. I'm sorry, it doesn't equal 2, it equals b. Our claim then is therefore, because f of x is between those h and g always, the limit as x approaches a of f of x is also b. So whatever that y value is, that's what it's going to be. Let me make sure that that answer remains visible when I box it. All right, so one example that's numeric, a related example that's slightly more generalized. Let's take a look at a specific function. So here's some kind of elaborate instructions. Use a graphing calculator to graph the given function and the equations y equals absolute value of x and y equals negative absolute value of x on the same coordinate plane. And I've got a plane down here, so I'll use that plane. Use the graphs to observe the squeeze theorem visually, then find the limit as x approaches 0 of f of x. And once we've done that, we want to write a sentence to state why we need the squeeze theorem to evaluate the given limit. Why do we force ourselves into that strategy? So let's just start. I want to graph this first one. So y equals absolute value of x. That's our g of x. So I'm just going to graph it here. So just taking a look at a table just to kind of remind ourselves how absolute value works. If I had x values -2 through +2, the absolute value of those numbers would be their distances from 0. So if g of x is just plain old absolute value of x, I can calculate g at -2 is the absolute value of -2. So how far is -2 from 0? Well, it's 2 away. So I get this point -2, +2. Same for -1. How far is -1 away from 0? It's 1 away. So the point's -1, 1. And I could write those out here as coordinate pairs, but you kind of see how the x values and the y values show up on the graph. If I take absolute value of 0, how far is 0 from 0? It's 0 away. So the origin's on that graph. And then the positive numbers are kind of easy. It's just whatever they are. Absolute value of 1, how far is 1 away from 0? It's 1 away. So that's the point 1, 1. And then absolute value of 2 is just 2. So 2, 2. And what we get when we connect those points is this kind of very linear V. And that is our absolute value function. Let me get that left side better. All right. Now I got to get the right side better. That's what happens when you try to get it right. Ooh, better. Let's also graph this y equals negative absolute value of x. So that's going to just tack on here as a third column. We'll call that one our h of x. And h of x equals negative absolute value of x. So basically what it's doing is it's giving the output where all these y values, they bump out of the absolute value positive, but then this negative on the outside turns them negative. So basically this is -2, -1, 0, -1, -2. I can graph those. So I've got -1, -1, -2, -2. I do have 0, 0. And then 1, -1, 2, -2. And that is h of x. So a little careful so I don't have to do it twice. So those are my two functions that I'm squeezing my other function in between. Let me label them. That's h of x equals negative absolute value of x. And then above, g of x equals just plain old, that's the parent function, absolute value of x. So the next instruction is for me to look at this function that we'll call our f of x. X times sine of 1 over x. And I'm told to do that in the graphing calculator. So I'm going to head over to Desmos to graph these. And I'll recreate our two absolute value functions over there. So here on Desmos, I'm going to type in g of x equals, and then absolute values, if I click the keypad, is there on the left. So absolute value of x. And then h of x is negative absolute value of x. And let me make sure I put an equals sign in there. Equals. And then let's graph the third function. So the one that we're really interested in, its limit. And as we put it in, f of x equals x times sine of 1 over x. We got to keep in mind, why do I have to use the squeeze theorem? So looking at these functions, I'm really interested in what's going on around 0. So it's kind of crowded in there as I look at the region near the origin. So what I'm going to do is I'm going to zoom in. And what I'm trying to find is what's happening to this x sine of 1 over x, the function that is graphed in the black line. So I'm going to just keep zooming in. So clearly this function is in between the two absolute value functions. But what I'm seeing is that no matter how far I zoom in, the graph is going up and down and up and down in smaller and smaller and smaller increments to where it almost looks solid. And this function, the x times sine of 1 over x, I cannot take its limit as x gets close to 0. Because no matter how far I zoom in, I'm not going to actually get a specific value at 0 because it's going up and down and up and down and up and down. Crazy function. Well, with that in mind, I'm going to hit home again just to get kind of another image of this picture. So I see that it has a horizontal asymptote at 1, and then it does this crazy oscillation in between kind of negative 0.75 and 0.75. So let's go back to our note screen to record that. So I'm going to graph this one. I'm going to put it in the lava. In fact, I'll put it in the red because that kind of matches what we're doing here. So horizontal asymptote at 1, as soon as it gets close to 0.75, it begins this crazy oscillation. So although the left and the right-hand sides of this function are really, they're kind of placid. They both kind of reach out and attain a value of 1. In the middle, it's anything but placid. It's totally up and down and up and down and up and down, closer and closer and closer and closer and closer. Well, let's calculate the limit of the red function. Because of the squeeze theorem, I can do it. So let's calculate the limits of the outside. So the limit as x approaches 0 of the absolute value of x equals the absolute value of 0, if I do direct substitution, equals 0. Similarly, the limit, if if I look at this lower h of x as x approaches 0 of negative absolute value of x, again, direct substitution, negative absolute value of 0 is 0. So what we're seeing is this statement, the limit as x approaches 0 of g of x equals the limit as x approaches 0 of h of x. And that value is 0. Since, and here's where we kind of make our claim about this, the squeeze theorem. Since g of x is less than or equal to f of x is less than or equal to h of x. So that's the initial condition. My red function's always between the purple and the blue one. The limit as x approaches 0 of x sine of 1 over x equals 0, and that's case closed. I really would box that whole statement. Our last task for this question is to give a sentence to say why we need the squeeze theorem to evaluate the given limit. And my sentence would go something like this. I cannot take the limit as x approaches 0 of x times sine of 1 over x by direct substitution. Comma, and other algebraic strategies are much more complicated than simply applying the squeeze theorem. Then simply applying the squeeze, or again, another name, the sandwich theorem. Period. So again, the bottom line with the squeeze theorem is it really allows us to calculate limits of functions that are otherwise really difficult or maybe impossible by other means. Thank you for joining. I'm going to leave this screen so you can take a look at it. We will see you soon. Bye for now.